Good morning, ladies and gentlemen. Welcome to this last appointment with this series of webinars dedicated to simulation apps. During this webinar, examples and case studies will be presented. The main body will be held by Mr. Riccardo Actis, CEO of ESRD, with a segment developed and presented by Edoardo Morandina from EngineSoft in collaboration with Brent Lancaster from ESRD, regarding a case study in the oil and gas industry and civil engineering. I want to say that it's been a pleasure for EngineSoft hosting our partner ESRD, and in particular Mr. Riccardo Actis, CEO of ESRD, for this series of webinars. If you missed the previous 3 webinars, they can be reviewed on the YouTube link in the webpage www.enginesoft.com/ESRD. Last reminder, you can follow news about the initiatives in the same webpage. Thank you very much, and I'll give the floor to Mr. Riccardo Actis.
Thank you, Luca, and welcome everybody to the webinar number 4, in which we'll be presenting case studies of simulation apps. First, let me review briefly the topics that we covered in the webinar, in the previous webinar, just to put the present webinar in context of the work that we have been doing over the last few weeks. In webinar number 1, we review the reasons why simulation has historically been performed by specialists and not by design engineers, and why legacy final element analysis methodology struggle with standardizing and automating simulation processes due to their inherent complexity, and particularly because of their inability to measure solution quality. And the next thing that we did back then was to define what were smart simulation apps, SYNAP for short, and why they're important, what are the benefits, and what are the challenges in creating and using them. Webinar 1 replay is available in the link indicated in this page. Then we move to webinar 2, in the simulation function, and that basically can be defined as knowledge capture, conceptualization, modeling, numerical approximation, and prediction, the process that is required to make decisions in the engineering decisions. Then we review the technical requirements for the development and deployment of smart engineering simulation apps that are simple, accurate, fast, efficient, and reliable. In other words, safer to use. And the replay of webinar 2 is available at the link indicated here. In webinar 3, we look at industry-specific portfolio simulation apps that were developed based on a new generation of simulation tools for analysis and design engineers that fit into existing analysis processes. We also review the FEA technology that is needed for the creation and deployment of the simulation apps that meet those technical requirements. And finally, we review a systematic approach for selection, creation, testing, and deployment of simulation apps, and we base that description on a typical aerospace and defense application. And as Luca mentioned, all these webinars, videos are available for review, and this is for number 3. Today, we are going to review some of the fundamentals of the underlying technology that enables the creation and deployment of reliable use of simulation apps. We are going to review an example case study, particularly is the applicability of simulation app for structural problems requiring accurate computation of a stress intensity factor for estimating the fatigue crack propagation life when residual stresses are present. Also, we have an example of simulation app case study for welded structures presented by EngineSoft. Let me start with a few words about ESRD. Engineering Software Research and Development was founded in 1989, and we have headquarters in St. Louis, Missouri, in the United States. We focus exclusively on computer-aided engineering, reliability through simulation governance, that is verification through the estimation and control of the error of approximation, validation through the estimation and control of the errors associated with the selection of mathematical models, and standardization through knowledge capture and simplicity. We develop engineering software for numerical simulation in the area of computational solid mechanics. We have been focused primarily in aerospace and defense applications, and over the last 10 years or so, a smart engineering simulation app for different industries. More information is available at www.esrd.com, and here you see the foundation of our technology can be reviewed and understood clearly by a recent book published by our founder, Dr. Parnasawa Ibobabushka, Finite Analysis. What is that ESRD offer in terms of software? We offer smart engineering simulation apps, which are engineering analysis tools developed under contract and for private licensing to industrial customers. We have commercial analysis products that provide the foundation for developing the applications. The main product, Stress Check Professional, is an advanced numerical simulation tool for FEA experts. Then we have CAE-Handbook, which is a customizable finite analysis solution for non-FEA experts, and the Toolbox, which is a specialized desktop application for non-finite analysis experts, and we will review briefly some of them during this presentation. And also, we offer the FEA solver technology for licensing. This is an example of a simulation app deployed in a digital CAE-Handbook. There is a family of apps that are available in a browser style, where the end user can select one object from the list and have a document explaining what the objective of that particular object is. Once the object is loaded, in this case, what we see is a detail of a structural connection. And you see here the solid model. And then after the solution is obtained, some result will be presented to the user in a very simple to use interface. The technology base on which this is the foundation of our product is a hierarchy modeling framework with hierarchy finite element spaces. What that means is that we have extremely simple element libraries where there is no need to search for the right element, and it has exact geometric representation. So the element is mapped into the geometry exactly. High resolution results are obtained from low density meshes. Continuous results are available throughout the model. Live post-processing with any function anywhere at any time, and automatic objective measure of accuracy. It's the only FEA implementation that was designed to support verification and validation procedures to enable the practice simulation governance. And we spoke about simulation governance also in the previous webinars. This FEA implementation was designed to obtain engineering results with minimal effort and assessment of reliability. We understood that most of the time the engineers spend in the software is to analyze and review the results. So that task should be extremely simple and to provide always assessment of quality. For that, a posterior error analysis based on a sequence of solution by increasing the order approximation on a fixed mesh is the mechanism to do that. That means that the extraction of any engineering quantity from any location in the model on the fly with convergence information, and is shown here in this example of a frame where the stress at the maximum location or the location of interest is computed for 3 different runs on a fixed mesh. And that shows the convergence of that particular data. Basically, it's the same mesh, and the use of hierarchy spaces allow us to increase the number of degrees of freedom without changing it. Here's an example of a simulation app in a finite element analysis toolbox. We call this the Stress Check Toolbox. There are several tools, and these tools are developed for the analysis of structural details with easy-to-use interfaces, while giving the analysts confidence in the computed data by providing convergence information for all the results that are presented. For example, there is one particular I want to mention briefly, the laminate Carrara analysis tool. And this tool was designed to support repair processes. When a composite material is damaged in service, this solution requires removing the damaged part, typically by performing a cutout that can be circular, elliptical, or racetrack, as shown here. And the part has to be shown to be good, even if the repair that goes after the cutout fails for certain loss levels. So the tool provides that information, and in a very simple to use interface for design engineers when they may have to make decisions on how the repair is going to be performed. What I'd like to present in more detail today is a case study of crack propagation from cold expanded holes. For those of you who are not familiar with the concept of cold expanded holes, in a cold expansion operation is simply inserting an oversized mandrel, as indicated here. The black object here represents the workpiece. This is a mandrel that is inserted into the hole with a sleeve, and when the mandrel is driven out of the workpiece, the part deforms radially, and residual stresses originate because the elastic stress distribution following the local plastic deformation of the expanded material near the edge of the hole compresses the plastic zone, creating a state of residual stresses as indicated here. What is the significance of this residual stress field is that cold expanded fastener holes provide substantial increase in fatigue life by reducing the rate of crack propagation that may initiate at the hole. Here you have a cross-section of a plate where the hole is located that has been cold work, and what we have been observing in practice is that crack at cold wall expanded holes evolve from a mandrel entrance side. And that is the area which is more difficult to detect. So the entrance side, the mandrel entrance on this side, exit on the other, and if the crack has the chance to form, it will happen at the entrance side. What happens typically is the outside surface is the one that is exposed, let's say the skin of an aircraft, and the inside is not easy to access. So crack may grow, become critical before they are detectable. Analysis processes are very complicated for this type of problems, even for experienced FEA analysts, which make it ideal for a simulation app. Just to give you an example of the class of crack propagation that may occur, this is from an experiment that was performed in which marker bands were used in the spectrum in order to be able to trace the crack front from an initial flaw on the entrance side. So this is this portion here magnified, and what you see is that the crack front grows substantially on the inner side, the not visible side of the part, before actually penetrates and is visible from the outside. In some occasions, this shape can be even more radical than this, and the crack can achieve critical size before even showing up on the outside. So the question was how to manage this in a way that is efficient, that is fast, that is accurate, and that provides reliable results. So a Sim app was developed to incorporate the beneficial effect of residual stresses due to the cold expansion in order to provide accurate computation of crack propagation lives. The idea was basically this: given the initial crack in a cold expanded hole, the spectrum loading, the material properties typically characterized by the modular elasticity Poisson ratio, and the rate of crack propagation as a function of the stress intensity factor, and the residual stress distribution. The goal is to compute the crack trajectory from the initial pre-crack to a critical size, find the curve of crack length as a function of the number of cycles, and the expected crack propagation life. So what we have done in this project was develop a simulation app that has a very simple interface and is organized as follows. In the first sequence of input, the information is the dimensions of the components are entered. In this case, we are simply showing a specimen type, but any kind of component can be incorporated into the system. When the dimensions, for example, in this particular case, we have those two options, straight holes or countersink holes, and depending on the choice, the user enters the information that is needed. This was one of the prerequisites, is that only show the input that is necessary based on the selection, so that the user never gets confused about what is important to enter and what data is not important, is irrelevant for the problem. Once the dimensions are entered, the selection of the material properties, and one of the requirements for this application was to have the ability to peruse and browse on material databases that provide information that is needed. As shown here, this is a typical PADN versus delta K curve for different load ratios. What that information is entered, another feature of the application is the ability to produce residual stress profiles for particular hole configuration. In this case, what the application will do is solve a elastoplastic problem using incremental theory of plasticity, and the user can specify the level of expansion, diametric interference, the material properties of the mandrel and on the plate is already available, and the characteristic of the elastoplastic material properties. One of the requirements that was important for this project was to recognize that when holes holes are cold worked, then they're typically filled with a fastener. And if some overload events occur during the life of the part, this overload and underload, that means positive or negative in terms of tension or compression, can produce change field. Module, what we accomplish is the ability to give the analyst the possibility of testing those hypotheses. If they detect that there is an overload event or an underload event important in the operation, they can see and recompute the residual stress distribution due to those. What information is there? The residual stress module allows the user to either import an existing residual stress from experimental data. This is what is called the user-provided residual stress, or a database residual stress. This is a database that is produced by the U.S. Air Force and is available at large for use. And this is a very extensive database of different materials and different hole diameter, different plate thickness, and different interference levels that are available for general use. Once the user selects that, then he defines the load. In this case, what we are seeing is a type of a spectrum load that it can be loaded, and the program will use it. And then the solved options are indicated here, where depending on the selection in the dimensions page, it will show where the location of the crack can be placed. For example, it can be in the knee of the countersink hole, or it can be in the corner. And once that is, all the information is there, the solve button is hit, and the program will perform all the necessary operations. What we are showing here are the typical outputs. What we see is an overview of all the steps during the crack propagation, and the summary is all the crack fronts. When one is selected from the list, the program will highlight which one you are selecting, and it will show the length on both surfaces. The other option is to look at the length versus cycle graph, and then will show the length of the crack as a function of the number of cycles. And there are two crack fronts, one along the bottom of what we call the surface, and one along the hole core. And this one is represented here. And when the same step number is selected, it shows with a dot where are they in the the fatigue crack propagation life. What is interesting to note that, which is a problem for the point of view of inspection of the cracks, is that the crack remains fairly small for a long time, and then all of a sudden it starts to grow very rapidly. So the precise or the accurate computation of these curves is important because that defines the inspection interval to catch the crack before it becomes critical. Another option that is available is to zoom in into a particular crack front and then get all the information about the stress intensity factor, the range of the stress intensity factor, the corresponding R ratio at the location of the crack front, and the rate of propagation at that particular point. We have gone through extensive validation process. Here showing one result of a validation test. The prediction is indicated by the two curves, the red and the black, that represent the two crack fronts. And this is the actual fatigue life where the specimen failed during the test. And here is a measured crack front shape. And what is seen is that the ability of the model to capture the actual shape of the crack is very good. And as you can see, these dots represent stages of crack propagation on the specimen, as measured from the fractographic evidence. In summary, this simulation app was developed and deployed in support of a program for the integration of residual stress analysis of critical fastener holes into the U.S. Air Force depot maintenance. The Sim App accounts for the beneficial effects of residual stresses in the calculation of fatigue life of cracking cold expanded holes. It's simple to use, accurate, fast, and reliable tool for expert and non-expert analysts. Provide excellent estimates of the crack propagation life, prediction, and the prediction of crack propagation maps are consistent with experimental observation. And importantly, also allows very quick assessment of different options of different core working procedures to get the light that is of interest in a very simple to use tool. And now I would like to give the floor to Engine to present a simulation app for welded structures. Here's a little preview of what you're going to see. And with that, I will please pass the control back to Luca.
Hello everybody. Now I'm here to present a particular structure, the welded node, which is used in offshore environment and also in a civil engineering environment to connect together hollow tubular section and open shape section joints, braces, all together. In particular, the structure we are going to present here is one used in the offshore environment. Here we can present the geometry of the structure composed by the body of the node and 8 incoming members. We can see from the figure up there, we see the numbering of the braces, and the geometry has been created in the code to configure the geometry, the constraints, and the loads. We create all the parameters to the handbook. Here we can set the loads and the constraints, and here we have the parameters. With this part, we can completely define the geometry configuration we want to analyze, and with the loads and constraints, we can set the particular configuration of boundary condition we want to analyze in particular. The handbook allows the user to define just the geometry you want to analyze and the boundary condition you want to analyze without having the problems of defining the mesh. And in particular, in this case, for example, we want to analyze the variation of these three parameters, which are the angles of the three incoming members, the 6, 7, and 8. And these are the boundary conditions used for the resolution of the problem. So we have a moment on the beam number 5, and we have some instructions on beam 8 and 4, and beam 3 and 2 and 1 have been fixed. In particular, as it's visible here, the handbook doesn't require the user to define the mesh, which is automatically generated by the code. And in particular, this takes advantage from the fact that using the P technology, we don't need to have a particular fine mesh in order to get accurate results. And in particular, these are three different geometrical configuration analyzed. As I said before, the user just needed to configure the particular problem we want to analyze in terms of loads and constraints and geometry, and it just need to press the solve button in order to get the results. And in particular, so it can have very accurate results due to the fact that the P technology doesn't require to have a very fine mesh in order to get the results. And we also have an instrument which permits the user to understand the errors committed during the analysis, and in order to understand if the results are good or no. In this case, for example, we can see that the error is quite low, and generally when the error is under the 3%, the analysis is a good analysis. So generally the results we got are accurate results.
Thank you, Eduardo, for the presentation of the work that you have been doing. One important consideration when developing simulation apps for cases like this, for example, is that the user is not involved in any decisions related to how to define the mesh density or how to apply boundary conditions, which is typically the situation of the target user of simulation apps, in which the is not expert in the numerical simulation. And that is done here by EngineSoft. That they understand the problem well, they can define it, they can encapsulate it, and they can deploy for use for non-experts. So I'd like to provide a brief summary of the main technology differentiator from simulation apps that our technology brings. Solution verification with automatic quality assurance is an inherent capability which is combined with direct, accurate geometric modeling. Also, one important consideration in the technology is the idealization is separate from the approximation. That permits, allows simple and minimal element library to capture topology, simple meshes to construct, check, revise, and use for simulation apps. It's feasible to use solid elements throughout, regardless of the thickness of the part. High fidelity multi-scale analysis are possible on the same mesh. High fidelity results for low resolution meshes are also possible. And what is very important is the ability to provide continuum solutions throughout the model, not just model. And the ability to perform light dynamic post-processing of results. And without the most critical aspect for the simulation apps is the objective measure of quality without an expert on call. For example, let's consider a small section of a portion of a wing of an aircraft contained between two ribs. If we zoom in into one of these areas, what you immediately notice on the right corner is the assembly consisting of several parts. In the center here, we have a spar that is connected to the other member by fasteners. In this case, there is a shear clip connected to the spar web by 5 fasteners. The other half of the shear clip is connected to the web of the rear spar of the rear frame. This frame in turn is what is bonded to the skin and the top and the bottom. And then the front part is also bolted to the spar by means of these fasteners that you identify here. Now, what is interesting to note about this problem is the scale. So we have a structural level. We are looking at the portion of the structure. Fasteners, which are very small in comparison to the rest of the structure. And to make things even more interesting, we are interested in assessing the influence of clearance in the result. The size of the clearance is very tiny in comparison with anything else. This is an example of the type of mesh that we're referring, and as example of differentiator, we are capable of performing multi-scale analysis on the same mesh. So we have the structural scale level and the local detail level of the stresses around the hull, including the effect of clearances. We use solid elements throughout. There is no shell-solid combination, which typically are source of problems and confusion that only expert can handle. And we have an accurate representation of modeling. As you can see, the mesh map exactly into the geometry. So as a concluding remarks, in the role of simulation apps, they provide a framework for the preservation and accumulation of institutional knowledge. They are for specialists and not experts alike, fit into existing analysis processes, capture best practices, and produce consistent results, removing the operator dependence. The benefits are making difficult classes of simulation problems easier, more accurate, and faster to solve by the specialists to support increasing complexity of products and demanding design cycles. Also, simulation app make routine classes of design analysis problems solvable by designers and engineers as they did for years when using handbooks and other design curves produced by method groups or regulation organizations. And finally, which is also very important, is empowering the new engineer to be productive sooner with access to reliable tools that have captured the institutional knowledge and the best practice of the organization. Finally, I would like to challenge you, do you have any idea for a simulation app? And if you do, you can contact me for more information or speak with the sponsor of this webinar series, EngineSoft. And with that, I would like to thank you for your attention and open the floor for any question that you might have.
Thank you very much, Ricardo. That's a very, very interesting presentation. And what was really clear was the easy to follow workflow to perform even very complex simulation in order to get reliable results. Again, I thank you very much, Ricardo. I thank you also, Eduardo, for this presentation. And this webinar has been the best way to close this series, giving an idea about the also how could be simple, even a technology even starting from a real complex problems. And I'd like to say to the audience that the new initiative will be defined in the next near future in order to go in depth with some aspects related with simulation apps. So please follow us through the web page. And thank you, and see you soon.